Section: Introduction. In this section, we discuss recent advancements in large language models, LLMs, that have led to impressive capabilities like answering questions, generating code, and reasoning. While the most powerful models typically run on cloud servers due to their need for high-performance GPUs, open-source providers have begun releasing smaller models with around 1 to 3 billion parameters that perform competitively. Additionally, consumer devices have become more powerful, allowing a 4-bit quantized 3 billion parameter model to decode 90 tokens per second on an Apple M3 laptop. These developments make it feasible to deploy LLMs directly on devices, which enhances privacy, allows for personalization with local data, and enables new approaches like hybrid inference that combines cloud and on-device processing. We find the web browser to be an ideal platform for on-device deployment for 3 main reasons. First, browsers naturally support tasks like managing calendars and responding to emails, which could be automated by browser-based agents. Second, browsers are universally accessible, requiring only a URL to use without additional software installation. Third, browsers simplify the complexities of different device backends, as technologies like WebGPU work across various devices without needing separate implementations for each. To take advantage of these opportunities, we introduce WebLLM, a high-performance in-browser LLM inference engine. This open-source JavaScript framework allows developers to deploy LLMs locally in the browser, integrating LLM capabilities into web applications easily. WebLLM provides an OpenAI-style API for straightforward integration, utilizes WebGPU and machine learning compilers for efficient GPU acceleration, employs WebAssembly for fast CPU computation, and supports web workers to keep back-end processes separate from the user interface. Our evaluation shows that WebLLM can achieve up to 80% of native performance, with potential for further improvement. WebLLM is structured to address 3 main challenges: creating a standardized API for easy integration, adapting to the browser's runtime environment, and ensuring efficient GPU acceleration. Its architecture consists of 3 components: a user-facing engine called Service Worker MLC engine, an encapsulated MLC engine in a web worker, and pre-compiled efficient WebGPU kernels. Web developers can instantiate the lightweight Service Worker MLC engine in their web applications, treating it like an endpoint. This engine loads an LLM as needed, processes OpenAI-style requests, and streams back responses for the web application to use. This familiar design offers several advantages, including well-defined behavior and easy integration into existing projects. It also allows for advanced features like structure generation, image input with vision language models, and loading multiple models for tasks like retrieval augmented generation. Unlike most LLM inference engines that use C++ or Python, we implemented WebLLM in JavaScript, requiring adaptation to browser technologies for optimal performance. To prevent heavy computations from blocking the user interface, we utilize web workers, which run in background threads. WebLLM consists of a lightweight front-end engine and a back-end engine in the worker thread, communicating through message passing with OpenAI requests and responses. For GPU acceleration, we leverage WebGPU, a JavaScript API that allows web applications to utilize the device's GPU. WebGPU is also back-end agnostic, meaning the same kernel can run on devices from different GPU vendors. We will discuss how these kernels are generated in more detail later. Section Summary. In this section, we introduce WebLLM, an open-source JavaScript framework that enables local deployment of large language models, LLMs, in web browsers, addressing challenges such as standardized APIs, browser adaptation, and efficient GPU acceleration. By utilizing web workers and WebGPU, WebLLM allows seamless integration of LLM capabilities into web applications while maintaining high performance and a familiar API structure. Section: WebAssembly. In this section, we discuss the role of WebAssembly in our approach. While having WebGPU is important, we recognize that large language model, LLM, inference also requires significant CPU computation. WebAssembly, or WASM, is a portable bytecode that we can compile from C++ and run in a JavaScript environment with performance close to native. Instead of rewriting CPU tasks in JavaScript, we utilize mscripton to compile high-performance C++ subsystems into WebAssembly for various CPU tasks in LLM inference. This includes components like a grammar engine for structure generation, sequence management in the paged key value cache, and tensor manipulation for executing kernels, allowing us to reuse C++ code without losing performance. Next, we highlight the importance of GPU acceleration for efficient LLM inference. WebGPU offers a standardized API for using GPUs in JavaScript and simplifies working with different GPU vendors. However, unlike native solutions like CUDA, WebGPU lacks optimized libraries for common GPU tasks, making it difficult to create high-performance custom GPU kernels such as paged attention and flash attention. We address this challenge by using machine learning compilation libraries like MLC-LLM and Apache TVM to compile effective WebGPU kernels. MLC-LLM takes open-source model implementations in Python, which utilize techniques like paged attention and flash attention, and compiles them for WebGPU. It also provides optimizations at both the graph and operator levels to enhance kernel performance. MLC-LLM produces two main outputs, converted weights and a WebAssembly library that includes both WebGPU kernels and other functions. For our evaluation, we compare the decoding speed of WebLLM, version 0.2.75, with MLC-LLM on the same Apple MacBook Pro M3 Max, using Chrome Canary. WebLLM employs WebGPU kernels alongside JavaScript and WebAssembly, while MLC-LLM uses Metal kernels with Python and C++. Our results indicate that WebLLM retains up to 80% of MLC-LLM's decoding speed. We see potential for further improvements by utilizing new WebGPU features and optimizing WebLLM's runtime.